Well, I think it's recording, and Joseph Breen is going to be giving the first talk about gluing a Morse flow line to itself. He's from UCLA.
Cool.
And I probably have to make you a co-host.
Oh, yeah, I was just going to ask.
Now you're a co-host.
Okay, cool. I was on a Zoom meeting earlier and my screen sharing was being very slow. So I'm hoping Zoom's woken up a little bit. But okay, so, well, first of all, thank you to Joe and Jacob for organizing and asking me to give the first talk. I'm also Joe. Hopefully it won't be too confusing for everyone. And I guess since I'm the inaugural seminar speaker, I want to start off with a quick maybe preview or introduction to what we'll be talking about, not only today, but maybe the point of some of the math to come. And maybe as far as references, I will say that this is mostly based off of some talks that Michael Hutchings has already given and some corresponding notes that Chris Gehrig wrote up. And I think links to those references are on the seminar website. So inevitably, when something I say doesn't make sense, you can probably go read about smarter people writing about it. Okay, but first, what are we doing here? What are we interested in? Why do we care? In case you wandered into this virtual seminar by accident, you don't know where you are. Also, I'll say at the beginning, I know that I have the handwriting of a 5th grader. I promise that I am actually a college graduate. So I'm aware, I'm working on it, I'm doing the best I can. But so presumably, if you didn't wander in here on accident, we are all at least in part Floer homologists of some kind. And many of you all are probably established, well-respected Floer homologists. Many of you are aspiring Floer homologists, or like me, you might be a wannabe poser Walmart brand Floer homologist, but whatever shape or size or mathematical aptitude we come in, there are a couple of things we care about. So things we care about as homologists. One of them, for example, is showing that d squared is 0 in our homology theory. Another thing that we care about is maybe showing that our homology theory actually is a topological invariant, right? Showing that it's a homotopy invariant. And the claim is that in either of these scenarios, there's probably more things you care about as a homologist, but probably if you can show these two things at the end of the day, you can sleep easy. So let's say these are the two things we care about for now. The claim is that in either of these scenarios, we care about broken flow lines. For example, if we want to show that d squared is 0, we have to study a moduli space of like index 2 flow lines or something. And then at the boundary, hopefully we get broken flow lines. The boundary. Or, for example, in the second scenario, if I want to show that this is a invariant under homotopy, maybe I have a homotopy of like a Morse function in a metric or something. And then for most times, this will be nice and Morse smale and generic, but there might be a certain time where things aren't generic or things aren't Morse smale. And so transversality fails and I have some weird broken flow line. So in a scenario like this, maybe at certain times, we have non-transverse weird broken flow lines. So in general, what we want to do when we talk about gluing flow lines is we want to understand the behavior of genuine flow lines nearby whatever broken flow lines we care about. So as far as I understand, when we talk about obstruction bundle gluing and when we talk about gluing flow lines together, we're considering broken flow lines and we're understanding the behavior of genuine flow lines nearby. And obstruction bundle gluing is going to be something relevant for this. Now, to be a little more particular, so we care about showing d squared is 0 and showing our homology theory's actual topological invariant. There are also some things that we like as homologists. Again, there's probably a lot of things I could write here. But one of them, which is central to pretty much everything in Morse theory, is transversality. And actually, so what I'm going to talk about today is I'm going to talk about a gluing scenario where we do actually have transversality, just to give you a heads up. But things that we don't always have. As homologists. Again, I could probably put a lot of things here. But in particular, for example, like in the second scenario up here, we might have a situation, my handwriting's so bad right now that I don't even know how to spell. You'll have situations where transversality fails. Yeah, okay, so this is Zoom being really slow. Sorry about that. I don't know if this is my internet, but it's got to catch up to me. Hopefully it's not a problem. And to parrot a comment that I don't claim to understand, so don't ask me about it, but obstruction bundle gluing is going to be relevant in scenarios where transversality fails. So for example, Hutchings says that obstruction bundle gluing is relevant when transversality fails, but maybe not too bad. I don't claim to really understand that. So I guess we'll see in this seminar what that means. Okay, so this is why we're here and what we're doing. Now, as far as what I'm going to talk about today, again, presumably most of the people here care about gluing things like holomorphic curves or things in actual floor theories. But to warm up to that, we're actually just going to spend today and then probably the next couple weeks in a finite dimensional regular Morse theory setting. We're going to see some of the gluing techniques applied in easier scenarios so that we can warm up to doing actual things that we probably care about. So as far as what I'm going to talk about today, to get you in the right mindset, this actually won't be too important for what I do, but I think what we want to be thinking about is circle-valued Morse theory. Yeah, sorry again. Zoom is really slow for me right now. So like I said, we're going to be in a finite dimensional Morse theory setting, but to introduce some of the phenomena that we'll care about, we're actually going to use circle-valued Morse theory. So I'll have a finite dimensional manifold X. And then I'll have a Morse function, which is S1 valued. Like I said, this will be interesting for the kind of phenomenon that we care about, but also because I think a lot of functionals that you come across on infinite dimensional manifolds in Floor theories might be naturally circle valued. And so first question is, Joe, what do you mean by a circle valued Morse function? Well, locally, this is a real valued function. So I won't write this down carefully, but by this I just mean locally Morse. And we want to do Morse homology. So, you know, we can try to do all the usual things that we do. Like I want to study critical points and flow lines, so I can pick a metric. The problem is when I go to set up And I guess I'll say this will give me a gradient. And so I can look at critical points and flow lines and all that good stuff. And I want to set up like a Morse chain complex as usual. The problem is that in this circle valued situation, there can be some weird scenarios where you have infinitely many flow lines between two critical points, and that's going to throw off how we count things. So the issue is that here, you can get infinitely many flow lines by like circling around the manifold many times. So we need to figure out how to deal with this to count things. So maybe to start drawing a picture. Here's my manifold X, excuse me. And I'm thinking about maybe the circle valuedness as being this way. The idea here is we could have two critical points, P, Q. And then, you know, maybe a flow line that goes like this. Flow line that wraps around 75 times or something. Flow line that wraps around a gazillion times. In general, between any two critical points, we could actually have infinitely many flow lines. So to deal with this, we use a different ring. We'll use the ring of power series. So to deal with this, maybe over Z, probably over Z mod 2, because orientations are hard. So this is formal power series in some variable t. And so we can use this as follows to define, for example, the differential. If I have a critical point P, I want to define my differential as, in the usual way, I'll sum over all of the critical points that have index smaller, one smaller than P. So all critical points Q such that the index of Q is one smaller than P. And I'll get something, some ring coefficient times Q. And this coefficient supposedly is going to live in this ring. So we should get a power series here. Do some purple. So what are the coefficients of this power series? What we do is we pick a regular value for the Morse function and look at the pre-image of that. So if theta is a regular value for f, look at, I'll call it sigma for now, I guess. Is the pre-image of that regular value. And for a given flow line, we can count how many times it intersects that submanifold. So the coefficient here is going to be, how do I write this to be consistent? The count of m sub k pq, where this thing is the count of flow lines between P and Q that intersect sigma k times. And so using this kind of differential and this kind of ring, now we can start doing Morse homology if I have an S1 valued Morse function. So this is maybe the mindset to be in. The other comment here is that a situation, maybe one reason why we want to consider this is because in S1 valued Morse theory, you can have a flow line, a non-trivial flow line between a point and itself. And I won't talk too much about this today. I think maybe Austin next week is going to talk more about this, or in the next couple of weeks we'll think more about this, but that's a situation that does not arise in real valued Morse theory. Like I said, the example that I'm going to spend most of the time doing doesn't actually use the S1 valued setup too much. But this is what the arena that we'll be in for the next couple of weeks. Okay. So what am I going to do? I guess this is section 3. Like I said, obstruction bundle gluing is going to be helpful for when we want to understand broken flow lines in a non-transverse scenario, but I'm going to warm up to that by showing you a gluing technique when we actually do have transversality. So what I'm going to spend most of the time doing is talking about gluing two flow lines that are actually transverse, but in a particular way that generalizes nicely to the type of stuff that we'll actually be doing when we talk about obstruction bundle gluing. Sorry, let me bring up the chat. So the question in the chat is, for this definition of the differential D, we have D squared equals 0 in homotopy invariance. Hopefully, yes. What is the homology? I don't want to say anything too incorrect, but yeah, I mean, this should give you a homology theory. I'm not actually going to show that, but I think the point of maybe the example that I'm about to do and the things that we'll talk about over the next couple weeks is like, what would we do to show that that's true? So for example, if we want to show that D squared is 0, we're going to have to understand broken flow lines, or we're going to have to look at like a boundary point of a moduli space. And the main example that I'm going to do is the gluing necessary to show that D squared is 0. So at the end of the day, yes, you should get genuine homology theory.
Right, but sorry, this is a very basic question. But in this example, what does the homology compute, like in terms of singular homology or whatever?
Yeah, so that's what I didn't want to say when be incorrect. Someone else can jump in. I don't know if it gives you something which is isomorphic to singular homology, or if it's something slightly different. I can't quite remember off the top of my head, to be honest. That's a good question. Yeah, at any point, anyone more knowledgeable than me can interject and give any insight. But like I said, so, you know, for example, if we wanted to show that D squared is 0, thank you, Morgan. So if we want to show that D squared is 0, like I mentioned, we have to study broken flow lines at the edge of some moduli space. So this is what I want to talk about. Let me say this. So suppose that we do have transversality. And we want to glue broken flow lines. For the purpose of showing that, for example, D squared is 0. I'll do a situation where we do have transversality, and then next week, Austin's going to turn it up a notch and talk about how to apply the techniques that I do here to a non-transverse scenario. So in particular, what we're working with is, let's say we have critical points P, Q, and R. This is maybe index I plus 1, index I, and index I minus 1. It's an R. I have flow lines between these, and we're going to use an upward gradient. I'll call these U minus and U plus. So where U plus and minus are flow lines of our Morse function. Okay. So first of all, what does it actually mean to be a flow line? The flow line equation is going to be, so U is a flow line if, so here I'll use an S coordinate on the R factor. So I want the S derivative of U minus the gradient of F of U to be 0. And then to save myself some writing and also to be consistent with Hutchings and the other references, I'm going to rename the gradient of F to be V so that I can save 0.1 seconds every time I have to write the gradient of F. And so then what we do is we consider the linearization of this equation. Or this will come up in a second. So get something like d sub u. This is going to eat a section of the pulled back tangent bundle. So tangent bundle over the flow line. And then eventually, so what's going to happen here in a bit is we want to use like a contraction mapping type argument. So we want a complete space. So we actually need to consider some Banach space completion of these things. And in Hutchings-Taubes, they do, so I could be wrong. I'm pretty sure this is a Sobolev space. I don't think it really matters for what we're talking about now, but I think this is like what I would call maybe H2, like an L2 Sobolev space. But we just need some Banach space completion of these things. Because like I said, eventually we want to do a contraction mapping argument.
I assume by H2 you meant H1.
Maybe.
One derivative.
Right. Yeah.
L2.
Thanks. Right. Yeah. The H is the 2 part. It's been a while since I've thought about Sobolev spaces. Thanks. So this linearization is going to eat one of these sections and spit out like a covariant derivative in the S thing, and then the covariant derivative of V in the psi direction. And the remark here, which again will come up later and it will be more important next week, I think, is that because we are in a transverse situation, this gives us surjectivity of this operator. Flow lines cut out transversely. Okay, so we'll come back to this in a second. But in order to glue, so in order to find a genuine flow line nearby this broken flow line, what we want to do is we kind of want to interpolate between this flow line and this other one. So this is what I think Hutchings calls a pre-gluing step. So first, we do this pre-gluing. Which, so by that I mean, as Zoom catches up to me, first of all, I'll pick a coordinate chart near my critical point Q. So the interpolation that I'm going to do is like at this transition point. So I'll pick a coordinate chart around Q. So pick a coordinate chart. Mostly just because I want to add things. So I need a coordinate chart to make addition make sense. And let's see, where am I? And then I pick a gluing parameter, which is going to be a large number, capital R. Okay, so then with this large parameter, I take each of these flow lines and I'm going to shift them. Oh, okay, so a chat comment for anyone watching the recording. I think I was wrong. The subscript 1 in L21 is because we're looking at sections of a bundle and not functions. Thank you. Yeah, I saw that notation and I tried reading through Hutchings-Taubes to figure out what L21 meant. And for anyone who wants to try this, reading through Hutchings-Taubes for 3 minutes is not a great way to absorb all the material. So that's what I thought. I assumed that an L2 subscript 1 meant that the 1 was for a derivative, so I thought it was like a Sobolev space, but maybe it's something else. In any case...
Yeah, I would agree with what you thought. I can't imagine what else could make sense there.
Yeah, in any case, I don't think it really matters. And at least in Hutchings' talks and his notes and stuff, he seems to kind of brush off the exact space. And I think just what's more important is that you have some Banach space completion. Yeah. I had never seen L21 as a Sobolev space notation though, like that before. In any case, yeah, no worries, thank you. All right, so I have this gluing parameter, and with this gluing parameter, I'm going to shift the flow lines. So how do I want to write this? I will let U superscript R, this is going to be U plus shifted up by R over 2. I think that's what I want. Yeah. Likewise for U minus. So what's the point here? The point of doing this shifting is that, so when S is close to 0, we want to be really close to the critical point Q. That's what this shifting is accomplishing. Maybe let me write that down. So near S equals 0, close to Q. And then again, to be consistent with the references and to save myself from writing the amount of letters that I'll have to be writing, I'm going to be a programmer and I'll rename U plus and minus to be these shifted things. So if that makes sense, I'm just going to drop the R for now, and I've already shifted these things, and I'll just use U plus and minus to denote the shifted flow lines. Okay, so we've shifted so that near S equals 0, each of these flow lines are very close to the critical point Q, and then to interpolate between them, we're going to use some cutoff functions. So next I'll choose cutoff functions beta plus and minus as follows. So I'll just draw a picture of them. Here's S. Here's S equals 0. Here's S equals R over 2. And here's negative R over 2. So beta minus is going to look like this. It'll be 1 to the left of negative r over 2, and then it'll decay to 0. Nope, sorry. So it's going to be 1 for all negative numbers, and then it'll decay to 0, like that. And then you can probably guess what beta plus is going to look like. And the only thing that I think we want to require about these cutoff functions is that their derivatives are on the order of 1 over r or something like that. Oops. So where the derivatives of these are on the order of 1 over r. So now with these things, I can kind of smoothly interpolate between my two flow lines to get a pre-glued thing, which is probably not actually a flow line yet, but the pre-glued flow line is going to look like beta minus times u minus plus beta plus times u plus, where again, this addition is being done in the coordinate chart nearby u that I picked. Nearby q, excuse me. So all I'm doing here is I have my coordinate chart and I have these interpolation functions. I'm just smoothly interpolating between them. Sorry. Now, I think usually what you would want to do here, so we're going to do something slightly different than usual, but usually we would pre-glue. So question, do we require partition of unity? No, I don't think so. Yeah, I don't believe so. I think they just have to satisfy these decay properties. So normally I think if you wanted to do this gluing where you find a genuine flow line nearby, you would do this pre-gluing, and then it's probably not actually a flow line. So then what you do is you perturb the pre-glued thing to figure out if you can get a flow line. So usually we would pre-glue and then perturb, but that's not what we're going to do here. With an eye towards the techniques that are relevant for this obstruction bundle gluing stuff, we're going to flip the order. And actually what I want to do is I want to perturb each of the flow lines individually first, and then pre-glue those, and then see if I can get an actual flow line. So instead, sorry, give me a sec. My other monitor is frozen, so I can't see my notes. That's okay. So instead what we want to do is perturb and then pre-glue. So by this I mean I'm going to let psi plus or minus be small sections of whatever our Banach space is, or small elements of whatever our Banach space is. Maybe C0 small. And what I want to do is with psi plus and psi minus, I want to perturb U minus and U plus individually. Now I'll write something down that doesn't quite literally make sense, and then I'll tell you how to make sense of it. But what I want to consider is I'll take U minus, perturb it by psi minus. This is the part that doesn't make sense. Do the same thing with the pluses and then glue those together. Okay, let me.
There's no U actually in this picture, is there? There's U minus and U plus. Or did I fail?
Yeah, so the U minus is this guy and the U plus is that guy. Yeah.
I'm asking because you wrote psi plus minus in L12 of U star TX.
Oh,
I
sorry.
wonder,
Yeah.
yeah.
No, good catch.
Okay.
Probably should write that. Thank you. Okay, sorry. I am bringing up my notes again. They froze on me for some reason. Now, like I said, this expression that I wrote down technically doesn't really make sense, even with our coordinate chart, because the size are, you know, elements of this space. So what I actually mean here, and I'm just going to suppress this notation again to be consistent with the references, but really what we probably actually mean here is this is like, so I take an exponential map along U minus in the direction of, sorry. Probably what this means in the direction of psi minus. So psi minus is like a section of this tangent bundle over U. So I can take an exponential map to make this, push this actually on the manifold, and then in my coordinate chart, I can actually add things. But I won't write that, and I will just use this slightly incorrect, but morally correct notation. Likewise over here. And again, these psi's are just perturbations of our flow lines. And the question is, I want this to be a flow line. So I want this to be a flow line. So let me give it a name. Call this capital U. So I want our flow line operator applied to U to be 0. Okay, now, so we'll just compute this, sort of. The first remark I'll make is to simplify things that in the coordinate chart, I'll assume that V is linear. Because what I want to do when I apply this operator to this thing, I want to be able to distribute V linearly over all the terms. So what do we get? One of the good things about talking on Zoom that I couldn't otherwise do on a chalkboard is to spare all of you from watching me try to do this on the spot and then probably screw up. I wrote down what you get already, and I'll just talk us through it. Whoops. Let's do that. So it's basically just the product rule. I'm pretty good at calculus, but I'm not great, so I'd probably screw up if I try to do this on the spot. So it turns out that when you apply this operator to this equation, to this expression, you're going to get something like this. Now, where do all these things come from? For example, when you distribute the ds over this term, you're going to get an S derivative of beta minus, leave this thing alone, and then leave the beta minus alone. Sorry, Zoom is still catching up to me again. It's really far behind me right now. But that first line, if I just verbally talk through it, this is just coming from the product rule distributing the S derivative onto that first term. Likewise, it's really slow. Okay, I'll let it catch up and I'll just verbally talk through things. Likewise, the second line is coming from distributing the S derivative over the second term. The third and fourth lines are coming from distributing V, the gradient vector field, over the terms. Now these Q's here, so for example, yeah, this is really slow. Okay, so I'll just talk through it. So for example, in the third line, when you distribute the V, you'll get a V of U minus, then you'll get this covariant derivative. And then the Q terms are for quadratic error terms that arise outside of the coordinate chart, apparently. So I made this assumption where the V is linear in the coordinate chart, but I think you'll still get some random error terms that don't really matter so much. Yeah, so this, to be honest, this is something that still kind of confused me. Hutchings assumes that, at least in this exposition, that V is linear in the coordinate chart. So nearby Q, you don't have any error terms, but in general, you'll get some maybe weird quadratic error terms elsewhere. I think the point of a lot of this is that if we were actually doing this computation, there would be a whole lot of error terms that we would have to estimate away, but they probably don't matter at the end of the day. So morally, at least, these are the important terms. Okay, Zoom has finally caught up to me. So that's okay. Like I said, this nasty expression just comes from distributing these terms onto this. Now, the next thing that I can do here, so beta minus, just to remind you, beta minus was like 1 for all negative numbers, and beta plus was 1 for all positive numbers. So if you look at this term, for example, the support of the derivative of beta minus is all positive numbers. So I can multiply this term by a beta plus for free. Eventually, once Zoom catches up to me. I can multiply that term by beta plus for free, and then I can do the same thing down here. The support of the derivative of beta plus is negative numbers, is in the negative numbers, so I can multiply that term by a beta minus for free. Then, having done this, we can simplify a lot of stuff and cancel some things out. For example, let's see, so what can we do? Also, there's a leaf blower right outside of my window right now, so sorry if you can hear that. U minus is a flow line, so here we have a term like this, and then this. U minus is a flow line, so those cancel out. These are going to be 0. Likewise, U plus is a flow line. These are going to cancel out. And then I can group a couple terms to get this linearized operator that we talked about earlier. for example, sorry, let me do it this way. So if I group this term with, where's this? Come on, Zin. This term with this term, that's going to give us the linearized operator for u minus that I talked about earlier. And likewise, I'll group this term with this term to get the linearized operator for u plus. And so then after some more simplification, which I also already did so that you don't have to watch me try to do it on the spot. We're going to get an expression like this. So again, to maybe talk through it briefly, come on. Okay. I was going to try to aim for an 11:50 finish, but that might have to go another 5 minutes or something. So like these two terms combine to give us this operator. The squiggly terms give us the one upstairs, and then I've collected all the other terms. Okay. So in order for this to be a flow line, I want this whole thing on the right-hand side to be 0. And then I'm going to give these things some names. So in the top line, the quantity in the parentheses, I'm going to call this capital theta of psi minus psi plus. And likewise with the bottom thing, I'm going to call this capital theta plus and capital theta minus. And if we can get the right-hand side to be 0, then we have a flow line and we've glued. So here's the lemma. And this is where the contraction mapping stuff is going to come into play. This is ridiculous. I'm really sorry. I guess it's my internet that's being very slow. So the fact is that we can do this. In this transverse scenario, we can actually find psi minus and psi plus to make each of these theta functions 0 and therefore glue. So the lemma is for R sufficiently big, there exists a unique pair, psi plus and minus, in their respective Banach spaces that are orthogonal to the kernel of these linearized operators. Such that the theta functions are 0. And if theta functions are 0, then the whole right side is 0 and we've glued. So what's the idea of the proof? Very briefly in words, the idea of the proof is that we can pick R large enough to get some sort of contraction and then use a contraction mapping argument to find a unique solution. So in particular, if I look at, since I have it on the screen, sorry, theta minus being 0. This is the same thing as du minus psi minus plus ds beta plus blah, 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 blah. So while Zoom catches up to me, I'm just writing down in the past. Yes, so orthogonal means with respect to the L2 inner product. Thanks. So I get 0 here, or I want this to be 0. And since this operator is surjective, I can talk about an inverse operator from the target space, which I think I wrote as just L2 sections of this thing, to the complement of the kernel. The L2 orthogonal complement of the kernel. And so using that inverse operator, I can rewrite this equation a little bit to get psi minus, this would be du minus inverse of, let's see, can I do this in my head? Q minus of psi minus minus the S derivative of beta plus times U plus plus psi plus. So for the sake of time, I'll quickly talk through kind of the punchline here, and then I'll give a 1-second preview for maybe what's to come next week, and then we can call it quits. And I'll get the same, or the corresponding expression for psi plus. With the flipped signs. And Zoom is way behind me right now. I don't know what to do about this. So I'll verbally talk through again what the punchline is. So if you look at this as my other expression pops into existence, this is like a magic trick, I'm not writing anything. If you look at the first expression, finding a solution roughly corresponds to finding a fixed point of the right-hand side. Or I want to think about these together in tuples. So I'm looking for a fixed point of like the tuple of operators on the right-hand side. So to find a fixed point, I can do that with the contraction mapping theorem because I'm working in a Banach space. But I need things to be a contraction. So how do I guarantee that things are a contraction? So the point is that the Q terms, evidently if the size are chosen small enough, that part will be a contraction. The part that you maybe have to worry about being a contraction corresponds to these two terms. And this is where the R parameter comes into play. So the idea is that here, one of the things I required about these cutoff functions was that their derivatives was on the order of 1/r. So if I just pick R large enough, in particular, if I pick R larger than the operator norms of these inverse operators, then I can ensure that this tuple of right-hand side operators is a contraction. So maybe I'll write, I'll be really sloppy about this just because we're low on time. Right-hand side is a contraction. Since I wrote proof idea up at the top left, that gives me full freedom to be extremely sloppy and imprecise. So the tuple of operators defined by the right-hand side is a contraction given that R is big enough, and therefore by a contraction mapping theorem, we can find a pair psi minus psi plus such that the thetas are 0. And therefore, finally, we have glued and we have found a genuine flow line. Okay, so like I said, I'm almost out of time, so I'll finish with maybe a minute of verbal nonsense. Here we had a situation where our flow lines were cut out transversely, and we were able to do this perturbing and then pre-gluing stuff to find a genuine flow line by making these theta functions 0. So gluing corresponded to being able to make these theta functions 0. Next week, what Austin's going to talk about is a situation where we do not have transversality. And it turns out that when we don't have transversality, and therefore the corresponding linearized operator is not surjective, if we try to do this same kind of computation, you won't be able to make one of these thetas 0. And the lack of being able to make one of these theta functions 0, this is the obstruction in obstruction bundle gluing. So when transversality fails, you may not be able to glue because you can't make one of these theta functions 0. And I think from there, we'll be able to talk about actually defining the obstruction bundle and figuring out how to deal with that. So that was most of what I had for today. Sorry again about Zoom not playing very well with me this morning. I'll need to figure that out. So I'll stop there for now.